Hello. For this video lecture, we're going to be looking at some philosophy of biology, in particular, looking at attempts to come up with a proper account of what it is for something to be alive versus being dead or just being never alive. So why do we really need this sort of account? Well, biology as a field of science, to distinguish it from other fields, specifically to distinguish it from chemistry, it needs to be focused on living things. And so this is sort of a primary concept within the whole gigantic field of biology. It's a foundation for the paradigm, if we want to use that terminology from Thomas Kuhn. And it certainly guides research questions of all sorts. What is it that biologists are actually studying, for one thing? But then more specifically, if we're looking at the origins of life, we need to have an account of what it is to be alive so that we can identify that transition from just some kind of fancy chemistry to actual living chemistry, right? An actual living process of some kind, whether it's an individual organism or whatever it was like back during the initial origins of life on Earth. Similarly, if we're looking for life elsewhere on another place inside the solar system or beyond, we're looking for other kinds of life in the universe, then we need to, again, have an account of what it is to be alive so that we know what we're looking for and we don't miss it. We could come across something that's quite interesting, but then just not recognize that it's alive because we don't have a really good account of what it is for something to be alive, especially something unfamiliar, like life on another moon or a planet or something. And then also artificial life, whether it's computer programs or robots or whatever it might be, artificial intelligence or something like that being alive. How do we know that it's actually properly considered to be alive versus just an algorithm of some sort? Well, we would need to have a full account of what it is to be alive. So these are the reasons why it can be important. It's useful and interesting to have a proper account of what it is to be alive versus just kind of having a rough intuitive sense of what it is to be alive. So here's just saying in words, right, printed, what I've already been describing. Many introductory biology textbooks have an account of what it is to be alive. They might even claim to be providing a definition of life, but they at least provide characteristics of living organisms, of living things of one kind or another. And so they might have things like this. Something is alive when it responds to stimuli, it grows and reproduces. They may even say that it's got DNA, or it's made up of cells, or a certain kind of movement, though as we might talk about, that is problematic. Not everything that's alive actually moves in the relevant way. There's some kind of self-regulation, like a homeostasis or a metabolism. Those are the kinds of things that are often listed as characteristics of life, at least life as we know it. The upshot of Carol Cleland's work on this topic is that we should not be trying to come up with a definition of life. It's okay to come up with some rough and ready characteristics that we associate with life so that we can move forward in our research in biology and answering some of those interesting questions that we listed before. But coming up with a definition of life sort of locks in our account of what it is to be alive inappropriately, and we'll see what she means by that. So let's look at, to begin with, a dictionary definition. There's lots of different kinds of definition, though most people, when they think of a definition, they think of one coming from a dictionary. So here's a popular website, dictionary.com. And they define life as you can read it, the condition that distinguishes organisms from inorganic objects and dead organisms, being manifested by growth through metabolism, reproduction, and the power of adaptation to environment through changes originating internally. That might sound like a really great definition. Like, wow, you really captured what it is to be alive. But what we're really looking for, what Cleland is really interested in trying to find, is something that gives us a real deep insight into what it is to be alive, as we said, so that we can distinguish it from just fancy chemistry of some sort or alien life, something that's very unfamiliar. How will we recognize it as being alive? So we can imagine what it would be like if we really somehow didn't know what it meant to be alive. Like we were just completely unfamiliar with the concept of life and being alive. Would this definition be helpful? Well, let's look at it. The condition that distinguishes organisms from inorganic objects and dead organisms. Well, organic versus inorganic, that could be based simply on carbon chemistry. Lots of things that are based on carbon chemistry without being alive, so that's not the key. The key might be here, organisms, distinguishes organisms from dead organisms. Well, that might seem obvious, but what they're really saying there is it's distinguishing living organisms from dead organisms. If we don't already understand what it is to be alive, then we're not going to understand what that distinction really is. We're not going to understand even what it means to be dead, as opposed to being, as they call it, just a regular organism. It's implied there that it's living organisms. So there's something circular going on here. When we talk about a definition being circular, then what's going on is they're using the concept in the definition of that concept, or using that word in the definition of the word. So they're saying that life is what distinguishes living organisms from dead organisms. So that's not particularly helpful. When they talk about growth, lots of things grow. Crystals grow, clouds grow, mountains grow. So what kind of growth are they really talking about here? Obviously, they're talking about the growth of something that's alive. Well, if we don't already know what it is to be alive, then we won't understand the particular kind of growth that they're talking about. Similar for reproduction, lots of things get copied one way or another. They are talking about a particular kind of reproduction, the kind of reproduction that living organisms, as we know them, go through. And if you're not already familiar with what it is to be alive and not already familiar with living organisms on Earth, then you're not going to recognize what kind of reproduction they're talking about. Adaptation, things change and adapt to the environment. Not all of them are living. So ultimately, the problem here is that while this gives a good account of the usage of the term life, right, that word, how it's actually used in the English language, it doesn't give us a really good understanding of what it is to be alive if we don't already know what it is to be alive. So what we're looking for is something that gives us that deeper insight. So kind of theory that gives us that understanding that we can use to recognize unfamiliar things as being alive or not alive. All right, so maybe what we need is something like a scientific definition. Science is much more careful than dictionaries. And in fact, the previous considerations help us to understand why it's inappropriate to consult dictionary definitions when you're thinking of concepts in philosophy or science, because dictionaries give us the way things are used. They don't attempt to show you sort of a deeper understanding of what that concept really is so that you can use it for yourself. It's a good starting point, dictionaries are, but you shouldn't, for example, cite a dictionary in your academic essays. All right, so scientific definitions, maybe they're more promising. They're much more careful. They try to identify specific characteristics that help us to categorize items properly so that we know exactly what we're talking about. They try to be very precise. Still, though, for something like life, might not be a good idea because we run into this problem that all definitions tend to run into. But as we'll see, this is a particular problem for trying to define what life is. If a definition, whether it's a dictionary definition or a scientific definition, if it's too narrow, then what we mean is that it's too restrictive, that it's ruling some things out of the definition that should be included. And we'll see some examples here in a moment. On the other hand, a definition, either a dictionary definition or a scientific definition, could run the risk of being too wide, that it's too permissive. It's including things that should not be included. An example that was sort of a real life example that we saw in science was the definition of a planet, and in particular Pluto. We had the planets were defined very roughly as, these big objects that eventually we understood to be orbiting the sun. That seems natural enough, a good definition. It includes certainly Earth and Mars and Jupiter and Saturn and all of those, but it also included Pluto. Eventually, however, scientists recognized that that basic definition was too wide. It was including things that maybe should not actually be included in the definition of a planet. And so Pluto got excluded because there were so many other things out there that were very similar to Pluto that we were not really willing to consider to be full planets. And so or scientists, refined the definition of a planet. And so it's much more clear and precise of a definition now, but it turns out that it excludes Pluto. So the definition was too wide to begin with. When we apply this idea to biology, if we have a definition of life that's too narrow, then it could be that some things that are actually alive are ruled out by definition. Something that's a somewhat unusual form of life, or maybe it's a kind of life that exists on another planet. If we come up with a definition of life that's too narrow, it might exclude that other kind of life. So for example, if we include in the definition of life that it has to have DNA, well, there's some other kind of life on another planet that is very unlikely to use DNA. And so we wouldn't want to say, oh, well, yes, it's walking around and interacting with its environment very much like Earth life does, but it doesn't have DNA, so therefore it doesn't qualify as being alive. That's a little silly. So that indicates that we're relying on a definition that would be too narrow if we say that it's got to have DNA. Or an even greater risk when we're trying to define life is being too permissive, that is being too wide. We had an example with that with the dictionary definition, where we had something being organic. Well, if we say that it needs to be organic in order to be alive, or we use that as a distinguishing characteristic of life, well, that's too wide. Lots of things are organic without being alive. Or if we say that it uses energy in some way, or it changes or reproduces, again, that's going to be too wide because lots of things use energy or go through complex chemical reactions or get copied one way or another without being alive. So a lot of definitions of life that are used nowadays are either too restrictive, they're too narrow, or they're too wide. Here's some examples of some things that get miscategorized, or at least it's controversial as to whether they've been properly categorized. If we're too restrictive, we might rule out alien life, as I mentioned, or some kinds of artificial life. There might be some very fancy artificial intelligence or other sorts of computer software that maybe even now, but at least in the future, could be considered alive, but current definitions that rely on being cellular or organic or something like that would be far too restrictive. They would be too narrow to incorporate that kind of life. Viruses are a famous kind of borderline case. There's a lot of debate still over whether viruses should be considered alive or not alive. If we say that living things have to have an active metabolism, well, viruses don't have a metabolism. They can't have a metabolism. They're not, and they're not cellular. They're not made of cells. So if we include those kinds of things in a definition of life, then viruses automatically get ruled out. Or it could be too permissive, as we said, things like just simple fire. The burning of organic material is a chemical reaction that's actually quite similar to the actual metabolism that goes on inside of the cells of known life forms. The basic inputs and outputs of that chemical reaction are the same, but we wouldn't want to say that fire is alive. So if we rely on a definition that focuses on the metabolic processes of breaking down organic molecules to release energy, well, that's too wide. That's going to include things that really shouldn't be alive. complex reactions, adapting to their environment, responding to responding to stimuli. That's something that our computers do right now, and our phones and so on, our cellular devices. And so we wouldn't want to consider those alive. So that would be too wide if we focused on responding to external stimuli in complex ways. All right, so I think we get an idea of what it is to be either too narrow or too wide for a definition. Some recent attempts are listed here in the scientific literature, and all of these are good attempts, right? They're capturing something very interesting about known life, but they all end up being a little too wide or a little too narrow. And we have seen some practical effects of this, where the Viking mission in the mid-1970s landed on Mars and was trying to find life. They designed some pretty interesting experiments where they were trying to find if living organisms are present on the surface of Mars. But they designed those experiments with a particular definition of life in mind, a particular account of what it is to be alive that's based on Earth life. It was actually based on biochemical metabolic definition of Earth life. Then when they ran those experiments on Mars, Mars is a very different environment than the surface of the Earth. So the results of their experiments were pretty inconclusive. They were confusing because they were designed to detect Earth life, not just life in general. And how would you design a very specific experiment to detect an unknown form of life? Well, if the form of life is unknown, you don't know what its outputs are, what its inputs are, or how it works. How would you know how to detect it in a clear and convincing way? So it was just declared kind of inconclusive, and it really restricted the number of missions that NASA was willing to fund to try to specifically find life anywhere until quite recently. Some of the more recent missions to Mars have had kind of they were focused on geology and atmospheric science and so on, but they were also looking on the lookout for living things. And we'll come back to how they do that because Carol Cleland doesn't just say that we shouldn't define life and leave it there, because she recognizes that we do need some general idea of what living things are in order to go about trying to find it in the world. So she does have some positive suggestions that are going to come up later in this video. What we really need is a full theory of life, and Cleland calls that a philosophical or an ideal definition of life. And this can be similar to a scientific definition, but sometimes scientific definitions might rely on some surface characteristics to come up with a rough and ready practical way of distinguishing the things that we're interested in, the things that belong in the category that we're interested in, and what things belong outside that category. So a philosophical definition, an ideal definition, or a theory of life should get at the real essence of what this actually is, so that we get a true understanding of it, so that when we come across something that's unfamiliar, we can successfully categorize it as either belonging in this category, where the concept is appropriately applied to this new item that we've discovered, versus when it should be outside the category. And the most common way that we come up with a philosophical or ideal definition is to try to find necessary and sufficient conditions for belonging in that category. Obviously, the category we're talking about now is living things, things that are alive. So what are the necessary and sufficient conditions for something to be alive? This is something that is really common in analytic philosophy, to try to come up with necessary and sufficient conditions for something to belong in a category, or to gotta pause it here for just a moment. All right, a necessary condition is one that it has to be present in order for something to belong in a certain category. Or another way of saying that is that if that property or condition is absent in a particular item, then there's just no chance of it belonging in that category, even if it's got many of the other characteristics and many of the other properties that we consider to be necessary or common for something to belong in a particular category. If it's missing one of the necessary conditions, then it just can't belong. then sufficient conditions are the set of properties that something must have in order to fully and successfully belong in a particular category. This might be a little confusing when talked about it's kind of in general terms like this, so maybe we should look at an example. A real common example that people use when dealing with necessary and sufficient conditions is this concept of being a bachelor. Now, this is a human concept, right? It comes from human social institutions, obviously, especially marriage, but it's useful for thinking about what necessary and sufficient conditions are. So what are some necessary conditions for being a bachelor? Some conditions that are properties that a person must have in order to qualify, things that if they don't have that property, then they just cannot count as a bachelor. And what we want to do here is come up with a set of necessary and sufficient conditions that we can use to properly categorize all people as either bachelors or non-bachelors, that we don't have anybody that's miscategorized, right? We don't want to have an account here that's too wide and includes individuals that are not bachelors, but we also don't want it to be too narrow so that it excludes people that actually are bachelors. So what are some necessary conditions? Well, they need to be unmarried, and that's a basic concept, a basic part of the concept of being a bachelor. If somebody is married, well, they might have all the other characteristics we associate with bachelors, but if they're married, then they cannot be a bachelor. They do not belong in this category. This concept just does not apply to them anymore. So they have to be unmarried. They have to be male, right? Bachelor is a male term. More recently, the term bachelorette can be applied to females. So if somebody is not male, then they're not going to qualify as being a bachelor. So that seems like another necessary condition. And there might be others. A set of sufficient conditions, well, you have to be unmarried, you have to be male, might need to be adult, human, that's an interesting and important one, available for marriage, and we can go on and on. One of the reasons why this is a useful one to use in classes is you can come up with lots and lots and lots of different conditions that you can build onto the set of sufficient conditions so that you can have great confidence that you are accurately classifying all individuals as either a bachelor or a non-bachelor. You could also do that with some other things like being a hammer. What are some necessary conditions for being a hammer? What are the set of sufficient conditions for being a hammer? These are some possibilities if you want to pause and take a quick look at those, but we'll move on. The problem, this is great to try to come up with a philosophical definition or an ideal definition. This is, the real goal. If we really do this, like we did for bachelor, then we can really understand what it is to be a bachelor. Not just how the word bachelor gets used in the English language, like we might get from a dictionary, but we really understand what it is to be a bachelor so that we can have good confidence in ourselves and our ability to be able to properly classify people as either bachelors or non-bachelors. The problem, though, is that in order to come up with that kind of an account, a philosophical definition, a set of necessary and sufficient conditions, is that we need a lot of experience with items that do and do not belong in that category. For example, if, say, we're trying to come up with a set of necessary and sufficient conditions for being a chair, but the only chairs that we had available were the set of chairs that were in a particular classroom or in a particular school. Well, then we might say that it's necessary that it be made of wood. Perhaps all the chairs in this particular classroom are made of wood. And those are the only chairs that we've ever seen. Then we might be tempted to say, yes, it's a necessary condition for it to be made of wood because look, all the chairs are made of wood. And we might say that they have to have wheels because all the chairs in this particular classroom have wheels. And we look at all the chairs that we've ever seen have wheels. So we say, oh, yeah, definitely a necessary condition is that it's got to have wheels. Well, really, we have experience with more chairs than just those. So we can recognize that we're coming up with a definition, a set of necessary and sufficient conditions for being a chair that's far too narrow. because if we had greater experience with a wider diversity of chairs, we'd recognize that some of them have wheels, some don't, some are made of wood, some are made of other materials. So we would recognize that being made of wood and having wheels are definitely not necessary conditions. And we might do a better job of coming up with a set of necessary and sufficient conditions if we had a wider experience with all sorts of different chairs. So what are we doing here with life? What's our situation? The problem is that we really only have one example of life. Yes, there's a tremendous diversity of life on Earth, but ultimately it all came from the same origin, all have very similar characteristics, same basic metabolic pathways, same basic cellular construction, same basic set of organic molecules that are used. They all have the same genetic code. They all use DNA or at least RNA. So the kind of life that we're familiar with, yeah, there's a lot of variations on the theme, but it's still just one theme, right? It's one kind of life. Presumably, life could be quite different elsewhere on different planets with different environmental conditions. Life could be very, very different. So we're in this position where we really only have one example of life. What we need then are different examples of life in order to become more familiar with what all sorts of different life there can be. And that will put us in a better position to come up with the set of necessary and sufficient conditions for what it is to be alive. I'm going to bounce through some possibilities here quickly. There's some promising places in our solar system where there might be life, different kinds of artificial life, even some alternative life on Earth. Maybe right here on Earth, there are different forms of life with an independent origin that we could use to get a better insight into what it is to be alive. But here's our overall situation right now. So to have a good general account of life, that is to be able to properly come up with the set of necessary and sufficient conditions, we need more examples of life. But in order to find new examples of life, we need to be able to reliably recognize what is alive and what's not alive. And to reliably recognize what is alive and what's not alive, we need a good general account of life. But in order to have a good general account of life, we need more examples of life. So we're back to the first item here in this list. And so we're stuck in this circle, presumably. So how do we find new examples of life when we don't have a complete definition, right? A proper set of necessary and sufficient conditions for what it is to be alive. So here comes Cleland's positive suggestions for how to do that. What we should be doing is not specifically just going out and looking for things that are alive, because again, we don't have a full proper account of what it is to be alive that's going to apply generally to all forms of life that we might encounter. So instead, what she suggests is that we do kind of other regular science, right? When we're exploring other moons or planets or whatnot, that we just do our regular geology, regular mineralogy, regular atmospheric science, and so on, that is very common in all of these planetary missions. But while we're doing that, we keep an eye out for anomalies. And from the material on Thomas Kuhn, this term anomaly means something that doesn't fit into the paradigm, right? So there's paradigms of geology or atmospheric science or just chemistry in general. And if we find something, when we're doing our normal geology work, geology investigations on another planetary body or a moon or something like that, and we find something that just doesn't fit into our normal geology paradigm, then that could be a clue, right? We haven't positively identified it as being alive or not alive. It's just an anomaly, and it's worthwhile to do some follow-up studies to check what is this exactly. And it could be that the only way to account for this anomaly is through biology. That is, only something alive could generate this particular thing that we've discovered while doing our geology investigations. Here's some examples. So a while back, I believe it was big in the 1990s, there was a meteorite that was positive, that landed on Earth, that was positively identified as being a piece of Mars. That might sound fantastic, which it kind of is, but large objects were hitting the planets, for billions of years. Pieces of those planets go flying off. Some of them fall back to that planet, but some of them just escape and they just go into orbit around the sun, and then eventually they might hit another planetary body. And in this case, a piece of Mars was broken off a long time ago, wandered around in space, and then eventually hit Earth. And then we found it. And based on mineralogical investigation, we've identified this as having a mineralogical composition that's so similar to the Martian composition that we say, yeah, this is a piece of Mars. So when investigating this thing on a microscopic level, they found this image. And the thing in the center here looks kind of like a segmented something. Right? We've got identifiable, I'm not a geologist, I'm not a mineralogist, so I don't know exactly what these other minerals are. All I know is that these other things kind of in the periphery of this image were recognizable to geologists. But the thing in the middle is weird. It looks very similar to a segmented worm, maybe, but it's a little too small for what we think of as worms on Earth. So maybe this is even sort of cellular segmentations of some kind, where we do recognize on Earth there are bacteria, various other kinds of microorganisms that come together in these almost worm-like structures. So this is weird, something that geologists did not find in other rocks that they investigated on Earth, or even other things that they've investigated from Mars. And they thought, wow, did we just find a fossilized life form embedded in a Martian meteorite? This would indicate that was, at least, maybe still is, life on Mars. So this is an anomaly. And they didn't immediately say, oh, we found it, this is definitely evidence of life. They said this is something unusual and is worth following up on. They did follow up on it, and eventually they came to a consensus that there are non-biological ways of forming this kind of a mineralogical structure. And so most scientists that study this are convinced that this is not evidence of life on Mars, but it's a good example of the kind of thing that Cleland is talking about. Here's another example. People that are doing atmospheric studies on Mars, just normal atmospheric studies, they're not trying to find life, they're just seeing what's there. Well, there have been detections of methane on Mars in amounts that are very difficult to explain using known geology and known inorganic chemistry, non-biological chemistry. We do know that there are organisms on Earth that generate methane as a waste product. So we know that there are biological processes that can do this, but we didn't know of any non-biological processes that could generate this excess methane. So this is another thing. It's like, oh, this is an anomaly. This could be worth following up on. And this is not, the case has not been closed on this one. We certainly don't have like any kind of definitive account, definitive account of where this methane is coming from exactly. And we definitely have not said that this is definitely clear evidence of life, but it's a kind of an anomaly that we can follow up on. A similar thing happened in the atmosphere of Venus not too long ago. People that were studying the atmosphere of Venus found excess phosphine, which is another thing that's difficult to generate without biological processes. So it was an anomaly. Now this one kind of fizzled out because follow-up studies didn't find any phosphine at all. So it might have just been a mistaken reading of some kind. But again, it's the kind of thing that folks are on the lookout for. When we're talking about planets outside of our solar system, we have telescopes now that are good enough that if there is a planet going around another star and that planet moves in front of that star, the light from that star could shine through the atmosphere of that planet and come right to us, hit our telescope, and we can figure out what exact wavelengths of light are making it through that planet's atmosphere. We know what wavelengths of light are coming from that star when the planet's not in front of it. So then when the planet is in front of it, we can detect what kinds of wavelengths are being absorbed by the atmosphere of that planet. And in this method known as spectroscopy, we can identify specific molecules that are present in that atmosphere based on what wavelengths of light are absorbed by that atmosphere. And we know that oxygen, the O2 molecule, is very unstable. It tends not to show up in significant amounts unless something interesting is generating a lot of oxygen before it can be destroyed. So like in our atmosphere on Earth, we have a lot of oxygen, obviously. It's about 20% oxygen. If all life on Earth stopped, that oxygen would break down very quickly and it would go away. The only reason we have so much free oxygen in our atmosphere is because of living processes that are generating it, specifically photosynthesis. So if we found something like oxygen present in the atmosphere of a planet going around another star using this method, that would be an anomaly. It wouldn't conclusively prove that there's life on that planet, but it would be something interesting and worth following up on somehow. How do we do follow-up studies on that planet going around another star? Well, we'll cross that bridge when we come to it. All right, I will go ahead and stop there.